Welcome to our series on radome and bumper testing, where we cover everything you need to know about radome testing and the usage of the powerful quasi-optical tester. In this video, we handle a very sensitive topic, the instrument sensitivity. In the previous video, we were looking in the distinguishability between two objects, so we wanted to distinguish between two very close objects. What we now want to do is we want to detect an object that is very, very close to the noise floor. So looking again on this drawing, what we see here on the left-hand side, there's the amplitude defined and it's decreasing with the distance. So for a radar sensor, this is the typical target detection. So how far does this one target have to stand out from the noise floor? Again, the quasi-optical is a two-dimensional measurement. So what we see is these points, and we need to see in the colors how far do these have to stick out of the noise floor. Therefore, I brought a couple of samples with me. First sample is an 0.5 millimeter wire, which is a quite thin wire that is usually used in electronic circuits and also for heating wires in the radomes. This wire is measured in both the quasi-optical and also in a VNA setup just for comparison. The second measurement is a single layer of tape, and this is also measured in the quasi-optical. So the single layer of tape is directly on one of these verification plates. It's currently in the quasi-optical. So therefore, let's have a look at the result. What do the results look like? So we have this thin layer of tape. This tape is about 45 micrometers thick. So we are expecting a phase change of around about 2 degrees. We can see that also on the right-hand side, where we see the phase difference between no tape, which would be a line at 162 degrees, which is caused by this red plate, and the difference that is then additionally coming from 1 layer, 2 layer, 3 layer of tapes. So even 1 layer of tape can be clearly distinguished using the quasi-optical, which is a quite insignificant influence on the actual radome performance. Now let's have a look on what the wire looks like. So again, here we have the 0.5 millimeter wire, and in the center image where we have the face mask of the quasi-optical, we can again see, okay, by inspection, there is a quite significant influence of that one single wire in the field of view of the measurement. Also on the right-hand side, where we see the phase at the dotted line, so at the center of the measurement, we can see there is an around about 10 degree, 9 degree phase change that is caused by this very small wire. So that means, even though that wire is very thin, we can still detect it with the quasi-optical setup. So just for curiosity again, let's have a look at how this would look like with, for example, a quasi-optical approach or a single point measurement. So without the wire, again, we needed to fix the wire. So therefore we have the 16 degree phase change, which is caused by the RX. We have the 16 degrees without the wire, and we have 18.2 degrees with the wire. So that means we only have 2 degrees of phase change, a little less than 2 degrees even of phase change when we have the additional wire, which is not really a significant difference. So with a single point measurement, it's really hard to detect the influence of that wire. So another topic is when we have a look at this massive block of aluminium, which we have here on our left-hand side, which is the quasi-optical. So it's built for stability, built for durability, but still aluminium has a temperature coefficient of around about 24 by 10 to minus 6, 1 per Kelvin. So that means with changes in temperature, also the material changes its length. So just to give you an example, a full wavelength at 77 gigahertz is round about 4 millimeters. So that means 4 millimeters equals 360 degrees of phase. So 1 degree of phase is just round about 11 micrometers. So very, very small. Coming back to the temperature change, we assume the instrument is 50 centimeters in length. With the temperature coefficient, that means that with just the temperature change of only 1 degree, we already have a phase change of around 1 degree just caused by the temperature. So it means we need to normalize with changing temperature. So it doesn't mean we can't perform accurate measurement, it just means we need to normalize more often. And the second example just says the same. So if we normalize the instrument, for example, in a U shape, and then we rotate it by 90 degrees and measure in a C shape, then of course, just due to the sheer weight of the aluminium, it bends. So by positioning a weight of 1 kilogram on a massive block, 500 by 50 by 50 millimeters of aluminium, it causes the block to bend about 25 micrometers. Sounds like an insignificant bend, but keeping in mind that the phase, 1 degree phase, only corresponds to 11 degrees, 11 micrometers. This means that this 1 kilogram weight already has an influence of about 2 degrees of phase. So again, it doesn't mean that we can't perform measurements. You just need to keep it in mind and normalize more often, because, for example, if you normalize in U shape, then you measure in C shape, you have different influence of the gravity. So that means you need to normalize. Just keep it in mind and normalize as often as you can.